All right, so PID control. So what I'm going to do is kind of compare it with LQR control, right? So if you have LQR control and pole placement, pretty much the same thing, right? Except in the case of LQR, we kind of can easily decide what the poles that need to be placed are, right? So if I'm looking at LQR, what we have is we have a system. Sorry. I'm just going to use the continuous time form, right? And then we had a reference signal, and what we did is we compared the reference signal to a multiplied version of the entire states, right? We looked at the whole state and we compared it to the reference signal, right? Generated an error term and we fed that in here, and sometimes you have to also multiply this by another gain matrix so that it kind of tracks this reference signal, so we get the output. And by adjusting k, essentially what we've done is the input is going to be equal to minus xk, sorry, minus k, this will have to be plus, minus k into xk plus, I'll call this r, r into j, right? So what we did is we set the input of our system to this, right? Sorry. So we had, this is what we call, so this was our control law, right? Right. So this is also, since we're using the whole state of the system, is called full state feedback. Right. So in PID, it's a bit more simpler, right? What we're doing is, if you have a system, let me zoom out a bit. If we have our system like this, what we do is we take the output y, right? And then we have our reference signal where we want it to kind of refer to, and then what we do is we just take this whole output, just the output, because that's what we care about, and we compare it to this reference, right? Sorry. The blue turned a different color, sorry about that. Yeah, so we compare it with this reference and then we generate a error term, right? So your error is actually r minus y, right? And then what we do is, if we just want a proportional controller, all we are going to do is the input that we are going to apply to the system, which is u. So u is going to be equal to p times that error value, right? So if this error value is high, you're going to provide a higher input, right? So the inputs are generally the force you're applying into the system, right? So the input is generally kind of achieved using motors or things like that, right? Think about a robot with wheels, right? So the input into the system would be the amount of torque or the force the wheels will be providing, or the amount of velocity it's being providing the system, or something like that, right? So the higher the E is, if the error between your reference and your output is very high, it's going to supply more input, more actuation to the system, right? So then the system will start start moving, right? So this is in the case of a moving vehicle, right? So when it starts moving, let's say this is your goal point, this is your reference. In the beginning, your position is over here. It's so far away from your reference. This E value is very high, so it's going to generate a higher input and start moving faster, right? And then what's going to happen is this Y value, your output is getting closer and closer to the reference. So then this E is going to get smaller and smaller and smaller, and so your input is going to get smaller and smaller and smaller, and ultimately the idea is it will come to where you want it to come to, right? But the problem with the proportional controller is when this error becomes small and smaller and smaller and smaller, this input becomes so small that after a while it won't reach, it will come close to, it might come close to your ultimate reference but might not ultimately reach it, right? So actually let me write that down first, proportional controller, and then it's going to be a summation here, right? So you multiply this E by this, actually the normal notation is actually K. So this is normally the value you multiply it is called Kp, right? This is the proportional constant, right? So you multiply it by some Kp value, right? So what you would do to deal with this steady state, so where it comes and settles down is what we call the steady state, right? So remember what output looks like, right? If we give a step function and something like that, it would come like this and try to settle down somewhere, right? If that settling down value, there's a gap here, then we say there is a steady state error, right? Because this settling down value is what we call the steady state. So to deal with steady state issues, what we do is we integrate this error, right? So we add another term, right, where we integrate the error value, right? So what happens when you integrate the error value is it takes into account all these errors, right, and kind of finds the general trend that it existed before, right? It kind of captures the memory of the system, like how it has been behaving all this time, right? So what happens then is, since you're integrating these values, your the term here will start to add up, right? And that can help you overcome this steady state error and cause this to deal with that issue that we saw before, where it doesn't reach the reference, right? So what we do is we add that term, and that's the I part of the PID, right? So it's proportional, and then integral, and derivative, right? So here what we would have is Ki and the integration of E, right? And that gets added into this system as well. So your input is actually going to be the sum of that, right? But the problem with just having an integral is sometimes that summation might exceed things and it might overshoot your reference value, right? So if you look at the output, now this is where you want it to come and stop, but it might go and overshoot that and come back down and then settle down like this because of this integral term, right? So the integral term introduces a possible overshoot, right? Because it's adding all these values and this term might be large, so it might kind of overshoot the final answer, and we don't want that to happen either, right? Because then the car will go forward, back, and then kind of have to settle down like that. So to deal with that, we add the third term, right, which is the derivative term, which is dE by dt, right? So then we add the third term, which is kd dE by dt into that, and then we add that into the system as well, and that's the derivative term. So what the derivative term is doing is it's looking at the change in the error, right? So how is that error changing? So for example, when it's coming closer and closer to the reference, right, you can see that if it's going steeper, what you can do is you can control that kind of gradient using this term kd, right? So what you're essentially doing is kind of capturing the next, capturing the, essentially what you're doing is kind of predicting the future, because you're capturing the trend of the error, right? You're kind of looking at where is this error going, because when you do a derivative, what you're getting are the gradients of your error function, right? So by looking at that, if the gradient is very high, you can see that there is a steeper increase, faster increase of your error or faster decrease of your error, and then by adjusting this KD value, you can kind of control that, right? So in LQR control, this is what our control law look like. In PID, this is what our control law looks like, right? And the great thing about PID control is it's easier to tune. Sorry, it's not necessarily easier to tune, but it's more intuitive to understand, because what you're doing is you're really looking at the output straight away, and you're comparing it with your reference to kind of adjust these values. But what these values are have to be determined by you, right? Not you, I meant like by the person designing the controller, right? KP, KI, and KD has to be tuned by you, right? So what you normally do is you would set these values and look at the output. So you would use something like a step input, look at how the output is behaving, and kind of adjust these values. It's more of an art than like a straightforward way to do it, right? So this kind of goes back to what we were talking about before with Fuzzy's project. Basically, you will never get a perfect answer, right? Because these values will be hand-tuned, right? And what you can do is you'll have to spend some time tuning it so that it performs reasonably well in most cases, right? That's really all you can do, right? So one of the other benefits of PID over LQR control is in LQR, you'll have to definitely find this state space model, right? You'll have to find these A, B values, C values, and all that stuff, and then kind of do complete pole placement and things like that, right? So modeling these A and B values, you remember what it was like when we did the spring damper system, right? We modeled that system, right? But then if you're dealing with more complicated systems like multiple motors and all that stuff, like you'll have to model those systems just to use pole placement properly, right? And then you have to kind of look at the Q and R values and stuff and do it, right? Usually LQR control and pole placement, if you're doing a very, very professional level kind of controller, you would use something like this, right? Where you would, if you need like very high amount of control and things like that, right? While as if you are just doing like a general small project, a PID controller is much more easier to design, because all you need to do is look at the output, right? So if you have a sensor that measures the output that you want, like an encoder that measures velocity or something like that, you can always compare it with the value that you want to and very easily design a PID control, right? It's much more easier to do, right? So that's really the theory of it. There's a really great video that I posted in your pre-work, which there's a pretty good explanation and some examples of how all of this works. So hopefully you guys watch that as well. But yeah, that's the general gist of PID controllers. So let's actually jump into the question and see how we can use some of MATLAB's functions to do it, right? So can you guys try doing question 2? I'll give you guys 10 minutes. It's very easy. First of all, let me kind of explain these, right? So what is settling time? Settling time is basically how long it takes your output to come to the value that you want to, right? So let's say this is your output with respect to time, and this is where you want it to settle down, right? But it might go like this and then kind of oscillate and then reach its steady state. The time it takes to reach that is called your settling time, right? So obviously that's a parameter that you have to worry about, right? When you're trying to design a controller. Like how long does it take it to come to the place that I want it to come, right? Because this settling time is an important metric. These are some important metrics that you would look when you're designing your controller, especially if you're kind of tuning these values, right? KP, KI, and KD, because you'll be hand tuning them. You'll be putting different values, looking at the output, and seeing how it performs. So you need some sort of metrics to kind of look at, right? So one important metric is the settling time. Like how long does it take to reach the steady state value that I want it to do, right? So here what we're going to do is we're going to tune the PID controller. That means pick those KP, KI, and KD values so that this settling time is less than 2 seconds, right? And then the other metric we're going to look at is the overshoot. That is how much is it overshooting the final steady state value, right? That is how far away is it from the steady state, like how much is the maximum overshoot from there. So it's usually given by a percentage. So the percentage is basically this overshoot value compared to the total value, that total height of this output, right? So if I call this delta y and this your final output, so it's dy by y as a percentage, right? Actually, not this y, right? Your final steady state. How much of a percentage is your overshoot out of your entire steady state? And that is this value, right? So obviously it has to be small. We don't want it to kind of oscillate too much. And then the steady state error is what I talked about before, right? So it might not reach this final steady state that we want it to, right? So if this is where we want it to stop, even with an overshoot, it might go like this and then settle down somewhere here, right? So we want this error to be about 1% in this question. So in Fuzzy's example in her project, that's what's happening, right? She wants her Turtlebot to go to a certain goal location, right, with a controller, and it stops somewhere around here, not exactly where you want to stop, right? So there is a steady state error there, a small error like this, right? So you kind of have to tune it so that that steady state error falls under a certain like percentage or something like that is acceptable, right? So what you could do in your project, for example, is say, okay, I'm trying to design my controller to reach certain metrics, right, that I think is acceptable for my operating conditions of my robot. Like, for example, I want the robot to get to a certain place by a certain amount of time, right? So you have a settling time. You can talk about the overshoot, if there is an overshoot. You can also explain what is an acceptable steady state error for you, right? So because you will never get a perfect steady state answer, right? You get somewhere close to, like, you might reach like 0.001 or something like that if your control is good enough to do it, if you tuned it well enough. But I think like a 1% steady state error is reasonable, right? So like that, you can set, if you're designing a controller, you can talk about what sort of metrics like this. Usually these are the important metrics: settling time, overshoot, and steady state error. And you can say what those, you can try to tune your PID controller so that you get these acceptable steady state errors, right? So how you would normally do that is you would give some sort of step input, look at how it performs, right? So shall we do this question? I'll give you guys 10 minutes and try and do this question and tune the PID values so that it reaches these kind of conditions. There is a function called PID in MATLAB which helps you kind of set those constant values very easily. All right, try and do it in the next 10 minutes. So the first couple of steps is easy. You define your, state space model with these values. Use that SS function to create a state space. And then there's a function called PID where you input that state space model and you can set the KP, KI, KD values. and then provide a step input. Look at what the output looks like for those different KP, KI, KD values. Okay. And use your knowledge to tune it. Like what happens when the KP is too high or too low, right? KI would affect the overshooting value. KD will affect how quickly it kind of settles down. But the higher the KD, the more oscillations you get, right? Actually, I provided a link here in this document, which gives you, if you follow that link, it gives you this, goes to this site, right? This is a pretty good site to learn control theory by yourself if you want to, right? Because what they do is, here you get an introduction and a bunch of examples on the top side, right? If you pick the introduction, after that you can go in this horizontal level, right? So once you pick this vertical top column tab, you can look at the theory introduction about modeling, analysis, PID, and a bunch of other stuff here as well, right? And then if you pick one of these examples, let's say you want to look at motor position, you can then follow again the modeling, analysis, PID of that example, right? So I would suggest everyone read this introduction section and look at the modeling, analysis, and PID. Under the PID section, there's a nice little table here about how KP, KI, and KD affects rise time, overshoot, settling time, and steady state error, right? So having a good understanding about how each of these values affect these components will give you a better idea of how to tune it, whether to increase KP, whether to decrease KI, or whatever, right? And then if you want to actually see it working in an example, you can pick the top tab like this. You can look at how to model it, how to analyze it, and then how to use PID on that, right? So this site is pretty great. There's also Simulink links here as well. So it's a pretty good way of easily learning control theory. Okay, so I'll actually give you guys some time to do this question. Coding. Okay, so hold on. Alright, so what we're going to do is we're going to write out these matrices first, right? So we have these matrices, right? So this is your state vector. This is what does this mean? This is basically, if this is your state vector x, this entire term just means x dot, right? Right, so your A matrix is minus B over J, K over J, minus K over L, minus R over L, right? So A is going to be equal to minus B over J, K over J, minus K over L, and minus R over L. So that's our A matrix. What's our B matrix? It's just 0 and 1 over L, right? And then what's our C matrix? It's just 1, 0. Right, so we've created the A, B, C values, and basically what these J, B, and all that values are given here, right? So it's just a matter of copying those values and just writing them down. So after that, what we can do is create a state space model. This d has to be 0, so you just can say, just put a 0 here, right? So when you run this, you create a oops, sorry. I think d will have to be a 0 vector, no? Oh right, this is the problem. I put, yeah, okay. Actually d just can be 0 here. Yeah, there we go. Alright, so now we created the state space model for this motor, right? Again, how you get this model, I've given the link. Basically, they've derived it here in the modeling section. It's good to just read how they've kind of derived it as well, which is just using physics, right? And the relationship between torque and current and voltage and all that stuff, right? But it doesn't matter to us how it was modeled, but ultimately this is the model that we get, right? So after that, what we're going to do is we're going to actually what I'll do is I'll do this step by step. Let's look at what the proportional controller does, right? So it's very easy to design the controller, right? You just say PID, and you can put the KP, KI, KD values. If you just want to design a proportional controller, you can forget about these two values and just put the first argument will be the KP value, right? So let's look at how the proportional control affects it. Before that, let's look at what the step response of this open loop system is, right? That is without any sort of control. So if I just run this without the PID control, right, we haven't really affected anything yet, just the open loop system response to a so this is how it's performing, right? So if I give it a step input of 1, it's going in reaching 0.1. So we kind of want it to go closer to 1, right? So what we're going to do is we're going to create a proportional controller by multiplying the error. So here you can see it's like 0.1, and we want it to kind of be 10 times that maybe, right? So that it reaches 1. So we're going to start off with something like 10, and then we're going to say PID P, and then we're going to get the closed loop system, right? So the closed loop system is just essentially going to be you can use this function called feedback, right? So these two functions are what you would use to kind of help you with the closed loop control with PID, right? And how you use the feedback function is you just multiply that controller into your system, right? And then what we're going to do is we're going to look at the step input of that system, right? So what we did is we created a PID controller. We used the feedback function to create that feedback, and then if you multiply, if you run this and look at the step input of the closed loop system, what you will get is, hold on, let me close. By the way, I'll put all of these code up tonight, right, including last week's answers as well. I think I haven't put those answers yet. Actually, last week's stuff I put, yeah. So this week I'll put all the answers up. I'll put up this code and stuff. Anyway, if I run this, you can see that now the P controller has achieved a higher. It's closer to our step input's input value, which is 1. It's going to about 0.5, right? Which is not enough. So what we can do is we can increase it. We can tune it and see, okay, what happens if I increase the value. Now you can see that there is an overshoot that happens, right? So maybe we should decrease the value a bit. So maybe like 50 or something. you're still getting a bit of an overshoot, right? So by the way, what are the conditions that we need to reach now? We need a settling time of less than 2 seconds, right? So the cool thing in this graph that you can do is you can right click and look at these values. What is the settling time, for example? So this is the settling time, and you can see the settling time is less than 2 seconds, which is good, right? Right. I think you can yeah, you can look at all these different characteristics of the system, right? So this is the rise time. There's actually should be a thing where you can get the values straight away. Okay, sorry. Yeah, when you hover over it, you can see the value, right? So when you hover over it, it says the settling time is 0.5. This is the rise time is 0.15 and so on, right? And then the steady state is 0.833. It's pretty close to 1, but there is still quite a bit of an error, right? So let's see what happens when we add the items, right? So if I add ki into this, right? By the way, these values that I picked here is like after tuning it, the final kind of values that seem reasonable. Sorry, it's a capital K. So if I add the ki term here, you can see that there is a higher rise time here. So to kind of bring that down a bit, we can add a kd term. To adjust it, right? And then we get this nice graph where if you look at the, so I didn't go through the entire process of tuning this because it will be kind of like a trial and error process, right? You'll have to play around with these values to get something that you want that is reaches your steady state, which is 1, since you're looking at a step input, and you would want to look at the characteristics by just how quickly it comes to, for example, settle. You can do that by settling time, and you can see that it only took 0.25 seconds, right? Which is great because we want it to be less than 2 seconds, right? And it has done that. You can see that the overshoot is very, very low, which is also good because we don't want the system to kind of oscillate. We want the system to nicely come to the reference value that we want it to. And you can also look at what the steady state is, and you look here, the steady state final value is 1, which is pretty much what we want, right? So the steady state error is essentially 0, right? So it kind of falls into all of these criteria that we set ourselves to, right? So right now I've given you straight away the values of kp, ki, kd that actually achieves this, right? What you can do at home, and what I suggest that you guys do, is play around with these values and see how kp and ki and kd affect the final step input, right? How you can maybe control oscillations, how you can control rise time, settling time, and all those things, right? So as I mentioned before, how every factor affects each other is given in this under the PID section in introduction, right? Also, if you read this section about motor speed under PID, they go through how to kind of tune it as well, like what sort of steps they took to kind of tune it, right? So again, it's a trial and error kind of process. So you play around with these values a bit, and then you come to the final value that you want to, right? According to the characteristics that you want to achieve. So yeah, so for example, here it says, okay, if we increase kp, your rise time will decrease, right? That's obvious. It quickly reaches your steady state, but it increases your overshoot, right? Because for example, if your KP value is very, very high, even for a small error, it will give a massive input, right? And it might overshoot the final error, right? So increasing KP can either overshoot it. If KP is too small, it will undershoot, right? So that's how KP affects your final rise time, right? And your overshoot. Settling time doesn't get affected much. The steady state error decreases the more you increase KP, right? Then KI affects it this way, KD affects it this way, right? So you can play around with these values, look through these examples as well. So each of these examples in the PID section of it, they've kind of tuned the controllers, right? So if you have a controller section in your tutorial, in your final project, I think going through this and designing a PID controller will be the easiest thing to do in your project. So it will actually be a good experience to make a simple controller in your projects and stuff if you're trying to do that. Alright guys, so that's really it for PID. I hope that was helpful, and you guys can play around with these values and see how it affects everything. I'll give the code by tonight along with these videos and stuff, or tomorrow latest, because it takes a while for these, because sometimes I have to edit the videos and make them shorter and stuff, right? So yeah, hopefully by tomorrow at least the videos will be up, and I'll try and put up the answers by tonight or latest tomorrow.